Hey, and welcome to this summary series. I'm going to tell you what we're going to cover in this video. We're going to talk about absolute versus local extrema, increasing and decreasing functions, concavity, inflection points. We're going to talk about all the theorems, so like extreme value theorem, the derivative theorems for maximums, minimums, concavity, when to use what, and then we're going to talk about how all of those previous items relate to graphing and optimization. So this review is from a math professor's perspective. I am going to emphasize areas that I notice students forget, and I notice that a lot of students don't really like working with the theory, so I'm going to really try to draw your attention to certain areas that I think are kind of hard, and so just to kind of give you a heads up on it, if that makes sense. You can look in the description for time markers of all these topics and also suggested related content for anything in this video. This is a review, so I'm going to go through things kind of quickly, but if you want a deeper explanation, look in the description. And I highly recommend you follow up this video with my study series where I have lots of other practice problems. And otherwise, let's get to it. Enjoy the review. So let's start by talking about absolute versus local maximum minimums. So first, let's just compare the formal definitions for reference, because I really want you to understand, like, what is that subtlety that makes absolute versus local maximums. Okay, so just take a second to read this over with me. Don't worry too much about getting very deep into it. We're just noticing differences here. So a function f of x has a local maximum value at a point C within its domain if f of x is less than or equal to f of c for all x lying in some open interval containing c. Okay, so now I want to compare that to the local minimum. This almost looks like the same definition, except now there's just a little difference where all of your f of x's are going to be greater than that minimum point, which makes sense. And again, it's for all x lying in some open interval containing c. So remember that language. So now I want to compare this to absolute maximums and minimums. Actually, before I do that, I want to mention here, another word for local max and min would be relative extrema. Okay, so for absolute max and mins, so check this out. F of x has a maximum value, an absolute maximum value, at a point C if f of x is less than or equal to f of c for all c in the domain. And for the minimum value, very similar. So right, it's going to be f of x is greater than or equal to f of c for all c in the domain. So the difference between local versus absolute, with local, you have this like loosely defined for all x lying in some open interval, versus with absolute, it's for all. So just a little distinction there. Okay, and just to finish this out, so other words for absolute maximums and minimums would be like extreme values or global maxima and minima. And just visually kind of what's going on here. So in this case, this would be my absolute max, or this would be like my absolute min. So all the other points here are smaller than the max. All the other points here are larger than the min. And then if we want to compare that, just here's our locals, right? So it's like around some interval. So we see these humps, so we call them local, and same idea here. So you can have both locals and you can have absolutes all in one graph. That's totally possible. And then the last thing I want to talk about, which is something that's very often forgotten, are closed intervals. So closed intervals mean that, your graph kind of has these clear stopping points. Closed intervals always have an absolute max and min, always. And this is kind of interesting. I drew this graph just to really drive this home. This is just a line. So normally a line doesn't have an absolute max or min, but in the case of being a closed domain, it does. And so it is easiest to determine absolute max and min on closed intervals. So let's talk about how to find those in closed intervals first. So one thing that we've got to remember here, what is a critical point? How do you find critical points? Well, critical points of a function f of x are places where either f prime of x is 0 or undefined. So hopefully you've been pretty familiar with a critical point. And so this will then lead us into the extreme value theorem. So if f is continuous on a closed interval, then f has both a maximum and minimum value. So that's exactly what we were just looking at in that picture. This is a guarantee as long as you have a continuous function on that closed interval. So if you have a closed interval, it's very easy to find absolute extrema. It's so easy. All you have to do is find the critical points, and then you evaluate f at the critical points and the endpoints of that closed interval, And then you just take the largest and smallest of these values. So I bring this up because a lot of times people forget this, and then they start making, tables, and they're drawing all these comparisons, and they spend all this time when in reality, it's very quick to figure this out if you have a closed interval. So just some ways extreme values could occur, just kind of pointing this out and driving this home. You can pause these and look at these. These are all these different ways. You can have them occur at interior points, endpoints, whatever you want. So now one thing to note that is important about this, going back to this extreme value theorem, this part right here, this continuity, this is really important, because if you don't have this, then you are not guaranteed to have a maximum and minimum. You just have to use reasoning to figure this out. So then all bets are off, and now you've just got to kind of think through it. So what I want to do is I want to compare two examples to really drive this home. So does the extreme value theorem guarantee that f of x equals 1 over x will have an absolute min and max on the closed interval from -3 to 3? And if so, what are they? So thinking about the function 1 over x, you'll note that it does not exist at when x equals 0, right? So this is not continuous. So f of x is not continuous at x equals 0. So that's important to note in this case, because on this closed interval, this means that this function is not continuous. So the answer to this then is no, we are not guaranteed by the extreme value theorem, because we are not continuous. So now we've just got to think through this. Does it have an absolute max and min? And one way you can kind of reason your way through this is you can just kind of sketch the graph. So let me make some space. And let me draw the graph. So here is just a little sketch of the graph, and I drew in these pink dotted lines just to remind myself that this is a closed interval, so this is where the graph will end. And so you can see here now that the closer we get to 0 on each side, this just goes up to positive infinity, and this side goes down to negative infinity. So there is no max or min. So this is what I mean. Now, in some cases, this could happen. You could have a max or min, but just in this case, we do not. So we do not have any max or min, so we can just move on. Now, I want to compare this, though, to almost the same question, extreme value theorem for f of x is 1 over x on this closed interval from 1 to 5. Okay, from 1 to 5, this is a different question. So the only place where this function is not continuous is at 0. So this interval does not go over 0, right? So let's think about the sketch of this graph. So here's a little sketch of what 1 over x from 1 to 5 looks like. Again, I drew those pink lines just to remind myself this is a closed interval. So this function is continuous from 1 to 5. So now the extreme value theorem says, yes, we are guaranteed to have a max and a min. And just by looking at the graph in this case, I can really see where the max and min are. But let's go like the true, calculus route. So if I wanted to see, do I have any critical points in this interval? So I would take the derivative of this, which would be negative x to the negative 1/2, or sorry, negative 2. So this is negative 1 over x squared. So the only critical point here would be where x equals 0, and that's not, again, that's not in our closed interval. So in this case, there are no critical points on that closed interval. So then the only possible max and min would be the endpoints. And I can see now just by looking at this, this is the max, this is the min. So there's your answer. So my max in this case will be 1, 1, and my min will be 5 and 1/5. So this extreme value theorem, it really depends on the context of the problem. And I think this is one that it can seem very difficult if you don't know what it says. But if you understand what it says, it can be very straightforward. So this is definitely one that you want to practice and be familiar with for a test. All right, so moving on, let's talk about monotonicity. So monotonic is really just another way to say increasing or decreasing. And so, just the idea behind this. So here's my function. This is increasing, this is decreasing, this is increasing. If you ever forget that, you can always just think back to lines. So a line that has a positive slope is also increasing. A line that has a negative slope is decreasing. So it's like the same direction with increasing and decreasing. So from a calculus perspective, what makes a function increasing? That's really the important thing to remember. So it has to do with being on a particular interval, and you take a look at the derivative, and so suppose f prime of x is continuous on this closed interval and differentiable on the open interval. So if f prime of x is greater than 0 for each x in that interval, then it is increasing. So you are in some interval, you find that test point, you find it's greater than 0. That means on that interval, the whole function will be increasing. And then vice versa, if the value of the derivative is negative for one of the values in the interval, then the whole function is decreasing on that interval. So that's something hopefully you've kind of practiced a little bit. And then a lot of times people think of this in relation to the first derivative test for local extrema. So very similar start. So let f of x be a continuous differentiable function at every point in some interval except possibly at a critical point C. So here's the meat of this theorem that you really want to make sure you remember. So if f prime of x changes from a positive to a negative interval at around that point C, then we say f of x has a local max at C. So think about what it means to be from positive. So this would be positive to negative. So here would be my critical point right here. So this is going to then be a local maximum. So a lot of times people like to draw like the little picture alongside it. It's a nice visual reference. And then vice versa. So if we go from negative to positive, so negative to positive, then we have a minimum. And if the signs do not change, then there are no local extrema at that critical point C. And I also want to bring up here a very forgotten but also very important other derivative test. So this is the second derivative test for local extrema. I find that a lot of students do not fully understand this particular part, so I really want to emphasize this. There are two ways to find extrema, and for this other test, so you take a look at f double prime, and you find that critical point. So the critical point comes from the first derivative. So the critical point comes from the first derivative. And then instead of having to make a table and go through, increasing, decreasing, all that stuff, you can just plug that critical point right into the second derivative. If the second derivative, the value of the second derivative at that critical point is negative, then you have a local maximum at C. So think about what this means. So we haven't totally reviewed concavity yet, but if this is negative, that means that the function is concave down. So then that would mean at this point C, this must be a maximum. And then vice versa. So we have this critical point, we plug it in. If it is positive at the second derivative, that would mean that our function is concave up. So that would mean that we have a minimum here. So this test is super, super handy, but a lot of people forget it. And then there's another part of this. It is possible you could plug in that critical point and just get the value of 0, and then that means that the test failed. So then you have to go back to the first derivative test. So it's possible that C is neither a local min or max. You need to run another test. So you should definitely be comfortable with both of these tests. A lot of times students will just hold on to the first derivative test, but knowing which test to use in a certain situation saves time. So I want to compare this just for a moment. So for each function, let's use the first derivative test to find all extrema, and then we're going to use the second derivative test for extrema. And then we're going to find the intervals of increasing, decreasing. So we're just going to make sure we're familiar with both of these tests. Okay, so let's start with this first really basic function. I'm going to do a basic example and then a kind of tough example. So starting with the first derivative test. So I've got to find the first derivative. So the first derivative of this is 3x squared minus 3. Then I have to find my critical points. So I take 3x squared minus 3 and I set this equal to 0. I can factor out the 3. And so then I can factor this as x minus 1, x plus 1. So I have critical points at x equals 1 and x equals negative 1. So there are my two critical points. Okay, now the first derivative test, this is where we'd have to make a table now around kind of these critical points. So let me clear some space. Okay, so the domain of this function is all real numbers. So I'm going to create my table. So I'm going to have my intervals. So I've got this interval from -infinity to -1. I've got my next interval from -1 to 1, and then I've got this final interval from 1 to +infinity. So I've broken up the domain. And so then I'm going to have the sign of f prime in each one of those intervals. And then from there, I can make my conclusions. Okay, so if I select a point here, so let's say like I take -2. So if I plug -2 into this, am I going to have a positive or negative value? Well, the sign of f prime will be positive. And then if I choose a value between -1 to 1, so let's say 0. So if I plug 0 into f prime, this will end up being negative. This will equal -3, so the sign of this will be negative. And then finally, on this last part, so if I plug in, say, 2 again, this will end up being positive again. So we have our, this is increasing, decreasing, and increasing. Okay, so you need all of this for the first derivative test. And so then I can see here, so I go from increasing to decreasing, and here I go from decreasing to increasing. So what this means then is that -1 is a maximum, and really a local maximum, and then 1 is a minimum. So how do I know if these are absolute or local? Well, now you've got to think about just how this particular function works. And also you can take into account like this behavior here that you just found. So I'm not graphing this entire function yet, but if I just think about what has to happen if I go from increasing, decreasing to increasing. So if I just sketch this out, here's increasing, decreasing, increasing. It's going to be something like this, right? So this is the only way that this function can really work. So these have got to be local max and min. So that's like how you kind of determine what type of extrema you have. Okay. So that was the first part of this. So let me just note that. So I've got that here, and then let me clear some space. So now I want to use the second derivative test for extrema. So let's see, I'll find f double prime. So this is 6x, that's it. And then what I'm supposed to do is I'm supposed to plug each one of these critical points into this second derivative, okay? So if I take f double prime of 1, so all I really care about is this is positive or negative. So this is going to be positive. So what that means then is since this is positive, 1 is a minimum, which is exactly what I found here. The hardest part about this is I notice that students kind of flip-flop the interpretation of this. So make note cards for this if that's something that you need. And then if I do f double prime of -1, so this will be 6 times -1, so this will be less than 0. So since it's a negative, that indicates that -1 is a maximum. So we get literally the exact same conclusion from our first derivative test, but do you notice how much faster this was? Like this was instant. I didn't have to draw the whole table. So this is why you want to practice this second derivative test for extrema. It's just a lot faster, and sometimes you really need that time on a test. And then we already found from the first derivative test our intervals of increasing, decreasing. So I will just note those. So here was what we found from the table. Okay, so now let's just do one more example. So this is a harder one. This particular example tends to be very tricky for students. So I want to show you a couple of tricks for approaching a problem like this. So pro tip, I think it's easier to take the derivative of this function if you distribute this rational exponent. So I have to take the derivative of this. So this will be f prime of x. This is 5/3 x to the 2/3 minus, and then this, let's see, this will be 4/3 x to the -1/3. Okay, so here's the first part of this. Now, if you look at like different YouTube channels, everybody has a different way of kind of dealing with this form. Personally, I like to get rid of the fractions, and I like to refactor this. So I don't want any negative exponents, and I want to get rid of the fractions. So what I'm going to do is I'm going to factor out 1/3 x to the negative 1/3. And so then if I factor 1/3 out of this part here, this will give me just 5x. So remember, if I take x minus 1/3, that will get me to 2/3. And then this will be minus 4. Oops, just minus 4. That's it. Okay, so if this is something that you struggle with, I have several videos where I reviewed this specific skill. So I will drop some of those in the description. Okay, so now I need to find my critical points. So I have critical points at x equals 0. This does not exist at x equals 0, right? Because 0 in the denominator right here. And then also we will have a critical point at x equals 4/5, because 4/5 will make this part here equal 0. Okay, so I've got my critical points. Let me make some space. And now we need to create our table. So I need to think about what is the domain of this function here. So it would be all real numbers. So let me just set up the table. Okay, so in the interest of time, I just went ahead and set up the table. So I've got now all of my intervals. So let's see, if I choose, say, like a negative number in here and I plug that into f prime of x, is this going to end up being a positive or negative value? Well, if I take a negative value, this will be negative here, and then this will also be negative, so you have a negative times a negative, so this ends up becoming something positive. And then if I take something in between 0 and 4/5, so let's say I take like 1/5, so if I think about that, so if I plug 1/5 in here, this will be something positive, but if I plug 1/5 in here, this will be really 1 minus 4, so this will be something positive times something negative, so this will be negative ultimately. I don't have to know what the answer is, I just have to know the sign. And then finally, if I choose, I don't know, a larger number, let's say 1, this will be positive, this will be positive, positive times a positive gives me something positive. So then I've got, this is increasing, this is decreasing, and this is increasing. So here's our answer for part C right here, so increasing, decreasing, increasing. And then now I have to think about what is the deal with my maximum and minimums. So notice here at 0, so I do want to be careful as I'm kind of thinking through this. So this goes from increasing to decreasing, but at 0, the first derivative does not exist. So before I write down max or min, does 0 exist in the original function f? It does. So what situation would we have if the derivative does not exist at that point, but it exists in the original function? That's going to be a cusp. So we'll review that later on, but I just wanted to mention that. So we're going from increasing to decreasing, and actually more likely we're going to go from like increasing to decreasing. So 0 is a max, and then here I'm going from decreasing to increasing. So here 4/5 is a min. Okay. So now that I've got all that, we're going to compare that to the second derivative test. So let me clear some space. Okay, and I just noted over here that what our max and min were. Okay, so just as a reminder, so if I were to multiply this guy, distribute this back in, so the original form of the derivative that we had was 5/3 x to the 2/3 minus 4/3 x to the negative 1/3. So now if I take the second derivative of this guy, this is going to become 10/9 x to the negative 1/3 minus 4/9 x to the negative 4/3. And so once again, if I want to actually like factor this down and factor out like a common term, so in this case I want to factor out 1/9, so these both have a denominator of 9, so I'll factor out the 9. And then I'm going to factor out the largest negative exponent, so this x to the negative 4/3. So notice what happens if I factor out x to the negative 4/3. This is going to leave me with 10x, right? Because negative 4/3 plus 1 will give me negative 1/3. And then this just becomes minus 4. And so there's a just slightly better way to maybe factor that. Okay, so let me make some space. Okay, so there's that second derivative that we just factored. So now, remember, I want to take the two critical points that I found in that first derivative. So, oops, and I need to make this f double prime of 0. So if I plug f double prime o 0 into this, so what do I get? Well, I actually get that this does not exist, so this is going to be inconclusive, right? Because if I plug 0 in, then this is going to give me a 0 in the denominator, so the test is not maybe helpful this time. And then if I plug in f double prime of 4/5, so let's see, what do I get in that case? If I plug in 4/5, this will be positive, and this will be positive, so this ends up being greater than 0. So that implies that 4/5, since it's greater than 0, 4/5 is a minimum. Okay, so this is an example then where, again, it was faster to find that this was a minimum, but unfortunately the test was inconclusive this time. So the natural question I think that comes from this is, why choose one test over another? So I want to just do a quick comparison. So for the first derivative test for extrema, so you should use it, of course, if you're told to use it. If you need to find intervals of increasing or decreasing, then this is a good idea. And then you also will need to use this if the second derivative test for extrema fails, okay? So this will generally get the job done, but it does take longer. So when would you want to use the second derivative test for extrema? Well, you're going to want to use it if you're told to use it. Sometimes teachers will specifically state to use this, and I have to tell you, it really pains me when I tell a student to use this and then they use this test, because they usually won't get credit then. Second, you should use this test if you don't need to find intervals of increasing or decreasing. So don't create extra work for yourself if this is good enough. And then also, this is a great check to see if you really found the right values for the first derivative test. I would always use this as a quick check because it is very fast to use. Okay, so now let's talk concavity. So just visually, so we've got, this is what a graph looks like when it's concave down. This is what it looks like when it's concave up. And so the idea here is, so a graph can go from concave down to concave up, and then you have this point here. So that's where concavity changes. So that's the point of inflection. So for a differentiable function, so we have concave up if the first derivative is increasing, and another word for concave up is convex. And then concave down, so you have a graph is concave down if the first derivative is decreasing on some interval. So let's talk about, how do you find inflection points? So you want to look for where you have f double prime is equal to 0, or where f double prime fails to exist. And then if the concavity changes at that point, it is an inflection point. Although you do want to be just mindful also, if this point that fails to exist, make sure that it actually exists like on your graph. So now we have enough information to review graphing. So let's talk about the steps for graphing. So first you want to determine the domain of the graph and any symmetry. So the symmetry is really just, it's like a guide. It's going to help you figure out how much of the graph you really need, and it's just kind of a guidance for yourself. And for symmetry, you want to use the f of negative x test. So you plug in negative x into your function, and then you interpret the result. Okay, next you of course want to find the first and second derivatives. And then you want to determine the intervals of increasing, decreasing, and then any absolute or local extrema as best as you can. You want to determine concavity and any points of inflection. And then you want to plot all those relevant points. And that could include, by the way, x-intercepts and y-intercepts. If those are easy to find, you should plot those. And then finally, sketch the curve and then ensure that you have met all of the criteria from your previous steps. So this step always seems like the easiest, but I noticed that like a student will very often do all of these steps right, and then they won't check that they actually met all of the previous criteria, and then they'll mess up the graph. So just always take that extra second to make sure your graph reflects all of the previous steps, if that makes sense. So what we're going to do now, we're going to look at these two functions that we were just working with before, and we're going to use the second derivative test to determine the intervals of concavity. And then we're going to determine any inflection points, and then we're going to sketch the graph. Okay, so we're going back to the same function that we had before. So let me just write out what the first and second derivative were and the critical points and all that, just so that we don't have to repeat it. So this was our first and second derivative, and we already found our critical points. So we had x equals 1 was a minimum, x equals -1 was a maximum. So we've done some of the work for graphing already. We also know that the domain, we already kind of talked about this, the domain is all real numbers, so I'll note that here. So just so that I follow the steps, so if I just kind of remind you, the first thing that we want to do is really find the domain and any symmetry. And instead what we've kind of done so far is steps 2 and 3. So let me just double back here to step 1. So to test for symmetry, you're going to plug in just -x into this function. So if I plug in -x, I get -x cubed plus 3x plus 3. So that's what would happen if I plug in -x. And so the thing about this is, like, you would need either none of the signs to change or all of the signs to change to call this either even or odd. So notice this sign changed, this side changed, but this one did not. So this means that we have no symmetry. So I do just want to note that. So now let's talk about the concavity and inflection points. So I'll clear some space. So we have the second derivative here. So if I set the second derivative equal to 0, this will equal 0 when x equals 0. So this is probably going to be our inflection point. So then I'm going to set up another table around this critical point, like so. And so then I just need to know what is the sign of f double prime. So this is like my second derivative test for concavity now. So if I plug in a negative value into f double prime, the value of this will be negative. If I plug in a positive value into my second derivative, the value of the second derivative will be positive. So my conclusion then is that this is concave down, this is concave up. So now we have our intervals of concavity. This one is concave down, this one is concave up. And then because this goes from concave down to concave up, we know that 0 is an inflection point. So now we really have all the information that we need. So let me note this information and then we'll graph. So I'll make some space. Okay, so here is just my other information. I'll make a little graph. Okay, and so now the thing that you want to remember with all of these like inflection points that you found and critical points and all that, you need to plug these back into the original function f. So let me do that. So I'm going to have f of 1, that equals 1. F of -1, so if I plug this back into the original function, this will equal 5. F of 0 will be equal to 3. So these are a couple of points that I can pretty easily plot. So let's see, I've got 1, 1. I've got -1, 1, 2, 3, 4. Oops, I need a little more space. 5. So here's that maximum point. And then I have 0, 3. So there's my inflection point. Now, just to make my life maybe a little bit easier, I just take a moment to think of, are there any other points I could easily graph? Well, notice I already found the y-intercept by plugging in 0. And then sometimes this is easy, sometimes it's not. So just by looking at this, could you find the x-intercepts? So in this case, you would have to be able to like factor this. I can't easily factor this, so I'm not going to worry about the x-intercepts. Just when it's easy to find the x-intercepts, just do it because it gives you a couple other just places to mark. Okay, so remember, now from -infinity to -1, I need to be increasing. And then from -1 to 1, I'm decreasing. And then from 1 on, I'm increasing. And then you can also see that I've captured my concavity in this. So here is the graph. So now let's compare that graph to this graph. So we've already done quite a bit of work for this problem. So before I write anything else, let's just maybe cover symmetry here. So if I plug in -x, since I need to know that for graphing, so this is going to give me x times -x minus 2. So once again, so there's going to be no symmetry here. So let me now just repeat some of the information that we found earlier because we will need that for graphing. Okay, so here was our first and second derivative, and we already did all the work to figure out we had a max here and a min here. And then just remember, this point, the first derivative does not exist here, so we will have to compensate for that in the graph. Okay, so now I need to take this second derivative, and I'm going to set it equal to 0. So this will equal 0 when this part here equals 0, and that part right there will equal 0 when x equals 4 over 10, which is equal to 2 over 5. And then also this does not exist at x equals 0, so we will just note that. Okay, so now let's see, I guess I'll note those points here. So we've got 2 over 5 and x equals 0. So we know that x equals 0 is not going to be an inflection point, right? Because we already found that it's a max, so it won't make sense. But we probably do just want to kind of inspect what's going on with the concavity. So let me make some space and a table. Okay, so once again, so I've got all my intervals here now. So let's see, if I think about just any negative point, and if I were to plug it into f double prime, so what sign am I going to have of f double prime? So this will end up being something negative times something else that's negative. So this ends up becoming a positive, right? Negative times a negative makes a positive. Okay, so next, let's choose a point in here. How about 1/10? So if I plug in 1/10 into this function, so plugging 1/10 in here will be something positive. Plugging 1/10 in here, this will give me 1 minus 4, so this is something negative. So this ends up becoming something negative. So this is kind of interesting to note. And then if I choose, I don't know, any large positive number, this will be something positive times something positive, so then this goes back to being positive. So what I have here now is I have that this is going to be concave up, this is going to be concave down, and this is going to be concave up. So now we have something that's always kind of a conundrum, I guess. So 0 acts like a max. So we found it was a max, right? But now it also has these qualities of an inflection point. So this is really telling me now, so 0 does not exist on the first derivative or in the second derivative, but it does exist in the original function. So 0 is a legit point that is on this function. It just has like a very funky behavior, and that's what's telling me that there's going to be a cusp here. So we will make this look like a cusp from this information. And then here at 2/5, so I can see here at 2/5, this is definitely an inflection point. Okay, so let me just note that for both of these. So this is going to be like a cusp. So, and then here we're going to have that this is an inflection point. Okay, so I've also got my concavity intervals here, so we've answered part of the question, and so now we need to sketch the graph. So let me clear some space, and let me draw a graph. And now I need to plug all these points in. So if I plug in f of 0, I will get 0. So I'll mark 0, 0 right here. And then f of 4/5, this is going to give me negative 1.034. And then f of 2/5, this will equal negative 0.869 rounding. So let's see, 4/5, that would be somewhere around here, negative 1.034. So I'm just kind of making an estimate. And then 2/5, so we're going to be somewhere around here. Okay, so now we've got to really make sure that we take into account everything that this graph was asking us to do. So going up to 0, I need to be increasing, but I also need to be concave up. So that's kind of what's telling us that we have a cusp. So I am increasing and concave up. See how I've kind of drawn that concave up? And so remember, a derivative can't exist at a point. So if I draw a point here, that will mean that the point exists on the graph, but the first derivative would not exist. So that's what kind of tells me that I'm going the right way with this. So now I'm going to go down this way, and then at 2/5, that's my inflection point, and then I need to go back to being concave up. So I go concave down and then concave up, and then I go back increasing here at 4/5. And so there you have it. So I think I wish I would have made this look a little pointier. Maybe I'll draw the line like this. So this is a cusp right here. So as you can see, graphing kind of takes a while. So this is one of those things where, like, if you're trying to study this, I highly recommend that you study a lot of tough graphs and really try to get your hands dirty with some of the harder problems. It'll make you much better at graphing, but do recognize it's going to take you a while to get through it. So one more thing to talk about, let's talk about optimization. So usually with optimization, you're going to have one of two situations. You might have a closed domain. And so if you have a closed domain, you can use that extreme value theorem, and then you don't have to go through, you know, like doing all the derivative tests and all that stuff. You can just test the endpoints and the critical points. And if you don't have a closed domain, then you want to use the second derivative test for extrema, not the first derivative test for extrema. So if you do not have a closed domain, then you go to this route. You don't need to usually know what your intervals of increasing or decreasing are. So this will save you a lot of time if you go this route. So the big thing about optimization, in my opinion, is to really consider the domain, because that's what's going to really save you the most amount of time and let you decide kind of what route to go. A lot of problems have a closed domain, and then a lot of them let you use the second derivative test. So what I want to do here is I want to determine the rectangle of largest area that can be inscribed in a semicircle of radius 4. So I want to give myself some space for this, and let me draw that situation. Okay, so here's kind of the situation. I've got this semicircle, we've got the radius of 4 here, and then I need to inscribe this rectangle into this. So what I'm trying to do is I'm trying to find that largest area. So what I'm trying to do is I'm trying to maximize my area, and the area of a rectangle is just length times height. Okay, so now I have to figure out how do I describe length and height in terms of this graph here. So if I think about, say, this point right here, this is the point x comma y. So my length is described by, if this is x right here, so this is x from here to here, the entire length is 2x. So I'll note that my length is equal to 2x. And then my height is described by this y coordinate on the semicircle. And I would really like to figure out what is the equation then of this semicircle. So if you forget what that is, so the equation of a circle, remember, is just x squared plus y squared equals r squared. So this is the equation of a circle. So if you're trying to solve this for a semicircle, then you just solve it for y. So in this case, I'm going to have y squared equals, so I'll plug in 4 for the r. So this will be 16 minus x squared. So for a semicircle, this will just be the square root of 16 minus x squared. So this will be my height. Okay, so then I have the equation for area is 2x times the square root of 16 minus x squared. So I just need to take the derivative of this guy. Now let's just think slightly deeper with this. What is the domain of this? It is a closed domain. So your domain doesn't have to be perfect, but at a minimum, your length, so the length of your, the length has to be at least 0. It would be really silly if it was 0, but it has to be at least 0. And then it cannot exceed 4. Right, because that's our maximum radius. So this is definitely like our dimensions are going to be somewhere in this. So we have a closed domain, which means that we can just find the critical point of this and then consider basically the endpoints on the critical point, and basically we can tell, right, that the endpoints are not going to be the maximum or minimum, so it's going to be the critical point that will be the maximum for this problem. So let me clear some space. And now let's just take the derivative. Let's see, I'll draw a nicer A. So I've got to use the product rule here. It's a good old product rule. So this will be 2 times the square root of 16 minus x squared. And then this will be plus 2x times 1/2 times 16 minus x squared to the negative 1/2 times negative 2x. So we've got to simplify all of this. So this is going to take us a moment, and it's worth our time to simplify this because this problem gets a lot easier if we simplify. So let's see, this will become minus 2x squared over the square root of 16 minus x squared. Now what I want to do is I want to get rid of the denominator here, so I'm going to really multiply both parts of this problem by the square root of 16 minus x squared. So I'm literally going to distribute this to both parts of this problem, which will then give me, so this becomes 2 times just 16 minus x squared, and then this part will just become minus 2x squared. So now you can see that this will really simplify. So this will simplify then to negative 4x squared plus, let's see, 32. Cool. So now let's clear some space. And so I've got a prime. If I factor out the negative 4, this will become x squared minus 8. Okay, yeah. And so now I just have to figure out the critical points of this. And so just where does x squared minus 8 equals 0? So I have critical points at x equals the square root of 8 and x equals the negative square root of 8. However, the negative square root of 8 is not in the domain, so we don't need to consider this one. So this is basically our critical point. So now I just have to consider, since this is a closed domain, just consider what happens when I plug in each of these points. So a of 0 and a of 4 are equal to the same thing. They're both equal to 0. And then if I take a of the square root of 8, this will give me 16. And so here is the largest area. So 16 units squared would be the largest area. So you see how we got to use the extreme value theorem to kind of streamline what we needed to do here. So that's why really understanding what those theorems say is so helpful. So this really brings us now to the end of this video, but I just want to mention some other topics that you might want to review. So things I did not cover that could still be on a test would be like mean value theorem, Rolle's theorem, Newton's method, L'Hopital's rule, related rates, linearization. So if you're in my class, I've probably given you directions as to what sections you need to cover, but I'm just mentioning this in case anybody else watching this. I've noticed that calculus books do all kinds of different things. So this section can pop up in lots of different areas. So these could be other topics that you might need to review as well. So make sure that you go back and review all of those if you need to. And otherwise, thanks for watching, guys. If this was helpful, consider giving this video a like or hitting the subscribe button. Hopefully I'll see you guys in the Study with a Math Professor video, where I have lots of free practice problems that you can accompany with this.